They're right there for you. 3-1. Relations and functions. Okay, you've learned this before. This so you would have learned. You would have started the learning process on this one. If you took intermediate algebra at this college around 10-5. And then we would have jumped out of it for a little bit, then jump back in, jump back out. Okay. Well, now we're really going to start dealing with functions because that's really the mainstay of everything you really see mathematically moving forward. So let's kind of go through once again some definitions. Okay. Notice here this first part. Relations, domain, and range. You've done that. You've done domain and range. Okay. A relation is a set of ordered pairs. Okay. So we can think of the ordered pair of, let's say, A, B, or X, Y, or even something like height and time. Okay. Because they do relate together. Okay. Any set of ordered pairs automatically relates the first coordinates, okay, to the second set of coordinates. And these have special names. Obviously, the domain is the relation of the set of all first coordinates. Those are going to be your, for arbitrary reasons right now, are going to be the X values, but it depends on what's on that axis. What have they decided to name that? Okay. And the range is the relation is the set of all second coordinates. And for us right now, we're going to be using Y. Okay, or they'll use A and B, or like I said, or height and time. How does height, like if I threw a ball, how does height relate to time? Okay. And then we have functions. Okay. I'm going to give you a little kind of a graphic here in just a second. It's on your notes. I'm going to do the best I can on this. I draw way better at home on my iPad. Okay, a function is a relation which every element of the domain is paired with exactly one element of the range. Equivalently, a function is a relation which no two distinct ordered pairs have the same first coordinate. What that's saying, in less mathy ways, you can't have the same X value. Okay, it can't happen more than once. Okay. So if I have a set here, here's a set of all my X values. And let's say I have 1, 2, 3, and 4. Okay. And then here, notice I have Y values of, let's just say A, B, and C. Notice I could make an ordered pair of 1, comma, A. That's fine, right? I could also make one of 2, comma, B. I could also make one of 3, comma, C. I could also make one if I wanted to of 4, comma, C. Notice I didn't say anything about the Y values. But then here's where you get a problem. What if I have, say, something like 4 to C, sorry, that went to the same thing. 4 C, 4 to B. Notice 4 happened again. Okay, that would not be a function because the 4 happened twice. Okay, it doesn't matter about the Y's. All that matters is you cannot have the same X value twice. Now, graphically, it's very much easier to see. Okay. Now, on your homework, they may give you a whole bunch of ordered pairs. Okay. And they may say, is this a function? And you have to look through, just look through there and go, no, because X happened twice. If it doesn't happen twice, then you're okay. You do have a function. Okay. And that is important. Okay. What's nice is we have something called the vertical line test, though. So let's look at these first two. Notice I have one that's called a function, one that's not called a function. The reason the first one is a function is I have a horizontal line there, but notice if I do this, vertical line test says this: if I can draw a line anywhere on this function at any time. And notice that vertical line only hits that function at exactly one spot only. It never hits it twice. Then you have a function. Okay? Pretty straightforward, right? Notice if I turn that parabola on its side, which instead of something being x equals y, you're having something of y equals x. You're going to have this right here, 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 or even the one they give you. It happens twice. And we can't have that. Okay? One reason is this. Okay? Just to be honest. Eventually in math, what's going to happen is this. Well, it's going to happen right now. If I told you, hey, solve for x. Well, that's easy enough to do when you have something like this one right here, where I'm only going to have one x value. Okay? But if I said solve for x on this one, you could rightly look at me and go, which one? Okay? Because the problem here is there's two x values at that moment. So where do you go? Do you go up or do you go down? Okay? Now, because you're in a pre-calculus, though we call this college algebra, this is a pre-calculus class. As you get higher up in calculus or in math, you are given the tools mathematically to start bounding in these functions and go, well, yeah, but I still need to solve it. We can't just say things are unsolvable anymore, but we can bound them in and go, okay, I only want to solve from this spot to this spot and see what that function is doing in that area. But good news, you don't got to worry about that. That's not till calculus 3. So you're A-okay. Good so far? Let's look at one more. Notice this one. Just points. Would that be a function or not a function? Remember this, a function says this. You cannot have the same x value twice. It has to pass the vertical line test. Okay? Well, I think you're used to hearing the word function, seeing lines. It can be dots as well. Okay? Notice no matter what in here, no matter where I put a line, no x value happens twice. So you still have a function in this scenario, because if I listed all these points, couldn't you agree that I'd have -3, what, 2? And then I'd have what? -1, 0, and then I'd have 0, 2, and then 2, what? -4, and then what? 4, 0. Notice looking at every single, oops. What was that one? 3, -3. I do like my iPad because I can squeeze. Everybody use an iPad where you can squeeze the Apple Pen and it'll erase for you, and then you can just let it go. I do that on here. That's when you see me messing up. It's me squeezing and realizing, oh, you're not using your iPad right now. So notice, not one of these is the same. You have a function. Okay. So don't get hung up too much. Okay. What we're looking for with functions, and like I said, we're going to be getting deeper into this. Okay. Is we are wanting to make sure that no matter what happens, we do not have x values happen twice in there at all. Twice horizontally is fine. We have a different name for that, and you'll learn it later on. Okay. I think it's called, I'm going to guess right now. There are so many mathy words out there that even I forget them sometimes. Are we good with that? If I gave you a question on your midterm and said, is this a function? Could you tell me? Good, because you have a question on your midterm that asks you, is this a function? Okay. I want to kind of review us real quick because it did seem to be something that kind of hurt people in intermediate. Come in here very quickly, make it look a little nicer. Get rid of some of this. Okay. We do need to review something that they don't really hit too much on here. But do you remember domain and range? Okay. Looking at this first one, we're just going to look at this one. Though we can still, hear my words, just because something is not a function doesn't mean it doesn't have a domain and doesn't mean it doesn't have a range. Okay. Everything has a domain and range. Okay. Even a point has a domain and it has a range. Okay. This is a very small domain. It's a very small range. So when we look at this one, we know the domain, okay, is always the x values. We also have to remember that, how to put this? You can use the walking analogy. We always go from left to right. But it's always good to know that you're always going to, when you're doing domain range, you're going from negative infinity to positive infinity. Okay, always. That's your direction. You're coming from over here and you're going that direction. Where I see a lot of people having trouble is they get hooked up into these graphs and just say, okay, well, that's where this function is and that's it. No, this function goes off to infinity. Okay, so if I was going to do the domain and range on this one, what would be my domain for this one? All real numbers, exactly. Because look, if I'm coming from negative infinity and I'm going this direction and I'm walking along this line right here, going this direction, no matter where I look, okay, for this one, obviously I'm looking up the whole time. This line's going to be there the whole time. And so, okay, now you could put all real numbers, or you could also put negative infinity to positive infinity. Cox will take both answers. I'll take both answers. But now, the range. Range is this. Range, y values. Same as before. You're coming from negative infinity, going to positive infinity. Okay? That means bottom up. So if you were going in this direction here, you're starting down here. Can we all agree that right here, there's nothing going on? If you were climbing, nothing's happening. You're looking around, there is just a void. And then all of a sudden, what happens? What happens right there? You find a line, yeah. You get somewhere, you're like, oh, look at this. There's like a little bubble right here. Okay? So at that moment, can you all agree there's like you're inside the bubble and then you're outside, or you're outside the bubble, then you're inside the bubble. This, what you learned last year, would be your vertex. Okay? That's the lowest point on that graph. So what would be your range? A little hard to tell on this one, right? Maybe 3.5, more or less. Yeah, right? Let's say 3.5. Okay, so we got 3.5 to infinity. Problem is, how do I enclose that? I can't just put that.
Bracket.
Bracket where?
3.5.
Exactly. And then I would close that off. Right? And the reason we're closing off infinity with a parenthesis, what does that parenthesis say? You can never what? Include it. Exactly. It doesn't equal that ever. Okay? The bracket means it equals that right there. Okay? We're good on domain and range? Now, use your math brain. What is domain and range? Other than what I just told you about the values. We talked about relations, right? Obviously, on this graph right here, there are 2 points that you can see, plain as day. This one and this one. They graphed them. They're there they are. I see them, there they are. You're telling me with those 2 points, I know exactly what that function looks like? No. How many points are they actually giving us right here? An infinite amount, right? Okay. I want you to keep that in mind. Look at this one here. I give you two things. Two exact same things, actually. Okay? One of them you would have seen like this. Y is equal to 2x plus 3. That's fine and dandy, right? And if I gave you that, which is what you've been used to dealing with, you could come here and say this. Hey, let's make us a little chart here. Can I scroll down just a little bit so I have a little more room? And I can say, hey, let's find some points on that line. Let's pretend like you've never learned anything about slope-intercept form. I just said, hey, graph, give me 2 points. Okay. Well, we could do -1, obviously. And when you plug that in, what's going to happen? You're going to get y is equal to 2 times -1 plus 3. Well, that ends up being -2 plus 3, which gives us a 1. Simple enough math. We do the same thing with -2. 2 times -2 is going to give me -4 plus 3, which is going to give me what? -1. So there's some points. The 2, -1, I don't graph on here. Obviously, I did graph the 0, 3 because why? Because we know that from what we learned last class, that is the 0, comma b, isn't it? But that's fine. Using the y equals 2x plus 3, I've got a way to find a point here, a point here, a point here, and that's fine. We're going to still be doing that. What a function does is this. It says, hey, that's nice. Okay? You're giving me these points. Okay? Or the equation says this. You give me a point, I'll give you an answer. What a function does is this. It says, hey, give me all of them. Give me everything all at once. Okay? And so it does. It says, let's take out the y. Because can we all agree? Now here, I want you to take the logical step from what I just said here about domain and range. Domain is your x values, right? A function says this. Give me all the x's, and I'll give you what? All the y's. You give me a 0, I'll give you a 3. You give me a 1, I'll give you what? A 5. Okay? But give them all to me. And when you give them all to me, I'm going to give you every possible answer or a function, a machine that you can just pop out any answer you want because these things relate to each other. Hence, it's every point. Here is your domains. Here is the range. And when you give me this x value, this y value, and this x value, and this y value, and this x and this y, this is the shape you're going to get. Okay? And so that's why we write functions like this. Instead of a y, we're going to put f of x is equal to 2 over 3 plus 3. It doesn't mean we're still not going to solve. You're still going to have to solve for things on this, but now we're not restricted to saying, okay, well, let me just give you a point. Now the function is going to say, what is this at this point? Okay, so looking at the same numbers we used, we would say, hey, f of -1 is equal to 1. F of -2 is equal to -1. Because all I'm doing is just taking that f of -1 and plugging it in for x. Okay? That's all that's happening. Now, let me get it on a very much lower level. Not because you're stupid. You are not stupid. Okay? Think of functions. When you start thinking of functions, and then trust me, I'm helping you out on a midterm right now. Think of shapes. Okay? Like this function right here, this function. If I wanted to boil this function down to its just base function. Now this function, I've done some stuff too, right? I've said, hey, I'm going to increase its magnitude by 2, and then I'm also going to move it. So I've given it a slope, and I've kind of moved it along the graph a little bit. But if I boiled it down to just its bare, what is this? It would look like this. F of x is equal to x. Okay? Because x is just a line, isn't it? Okay? And I may have boiled it down a little bit too much, but still, if you think of it like a shape, you can look at that and go, I know that's a line because the professor has told us anytime we see a power of what? 1, we're going to have a line. So there you go. At its most basic, that's it. So I can actually do this too. If you've done this before, one of the very last things you graphed in intermediate was one of these. Well, we know now that right there is a function that is a parabola. So that's a quadratic function. So just looking at the function, you can go, okay, I don't know. Well, this one right here, you should know kind of what it looks like. Okay. I know it's a parabola. It's going up. That's all you need to know, really. No matter what I do to it now, you can go, okay, so that's a parabola. Okay, I can see that. So on your midterm, whenever I start giving you really funky looking functions, just look at the leading coefficient and go, oh, that's got to be this graph. It's got to be that. Now, I don't know all the behaviors it's going to do because I can make these things look really, really weird. You'll see one shortly. It's going to look really, really weird. It's going to be a negative x to the 8th power. Okay. And it just wiggles all over the place, like it's having like a little seizure. Okay. But you can see what it's doing. You can go, oh, once you learn these, you can go, I can kind of see it. I can see that graph and what's happening. By the end of chapter 3, you're really going to know what these guys are doing. So far, so good? Okay. Don't lose me on the graphs. Let's look at some of the graphs. Now, what you're going to be doing, some of your homework is going to be changing these y's. Okay, this y is equal to, or something is equal to something else. How we change something over to a function is we make it equal to y. Isn't that how we did slope-intercept form? Make y equals whatever, okay? Same thing. You got to get y alone. And then all you do at that point is change y to f of x. And you've now created a function, okay? So let's look at one. Take a look at that guy right there. He's ugly. And he's a combination of functions. Yes, you can have more than one function. You will learn all about that around in chapter 5, about how we can combine functions. But for right now, we have 4y plus the cube root of x is equal to x plus 4 squared. The name of the game is this. Get y alone. That's it. Get y by itself. This is pretty straightforward. While it looks messy, let's look at it carefully. Notice I've already got a y on the left-hand side. How about I take that y, okay, this right here, I'm going to take this and get part alone and take that guy right there, and let's subtract that cube root of x off both sides. Now we're left with 4y is equal to x plus 4 squared minus the cube root of x. What do I got to do that for? Yeah, just divide off that 4. What I do to one side, I do to the other side. And notice we're left here. Y is equal to the x plus 4 squared minus the cube root of x, all divided by 4. But the problem is that is not a function. Okay? So to make that a function, here's how hard it is. See that y? In fact, I'll use red so that way, in case you're looking there, get rid of the y and write it as f of x. And now you have a function. And that function says this. It says, now I've given you a function. Now, I'll be honest, this is an ugly, ugly function. I couldn't even imagine to tell you what the graph looks like on this one because it's a combination of a bunch of functions, okay? There's a quadratic, there's a cube root, and there's a fraction. So it's going to do some junk. Not worried about that. But now I can evaluate that function at any time. I really want you to get the concept of this. Why? Why do we care about that? Because I came over here, a very simple function is a quadratic function. You've done this a lot. Are you watching? Okay. If I said that this is times 0, good job. Notice that function says I have an upside down parabola. At some point in time, I was holding on to that marker that I threw. And then I tossed it, and then the time started. And then she caught it. Therefore, there are 2 times zeros whenever that pin was at the same level. Now, mathematically, that function keeps going, but when it goes down below a certain point, don't worry about it. But if you're doing some modeling over real world things, I could say, hey, if I want to change my X and Y axes to height and time, height being the Y, X being the T value, I have a function called h of t, height with respect to time. So don't get used to f of x. You can see g of x, h of t, no matter what, okay? But I could say, since I have this function that I can look at and go, I wonder how high that pin was at time 0.5. With this function, I can plug in, oh, well, what's h of 0.5? I plug it in, I do the math. Oh, it was this high at that point. That's what functions allow us to do. Okay? They allow us to solve real world things, model real things, and that's exactly what people do. I get a lot of data. I'm going statistics class on you real fast. What are you taking in college? What's like your major?
Early childhood education.
Perfect. I know this because my wife teaches second grade. My wife comes home with graphs all the time because they never really teach you how to read graphs. Okay. So she comes with all this information, but all this data usually creates a shape. Okay. And what can happen sometimes if we see enough data, a lot of data. I mean, we're talking just tons. Can't even just really, like, sometimes a shape comes out of it. And we could take these functions that we learned about, even in this class, and go, how can I create a graph that kind of flows with this so I can kind of model what's happening? So you can start looking at your students going, when I spend this much time doing this lesson with Savas or was into math, I see this, I see a curve, I see an exponential curve. I wonder if, and then you can start playing. That's how functions work. Okay. Kind of get it a little bit better, like at least conceptually, a little bit why. It's not just math for math's sake. I get it in college algebra, it usually is. Okay. So notice this one right here. It says, hey, once you do it, solve for -3. That's fine, because I do this, and this is how we write it. F of -3, where x is equal to -3. If I went over to -3, where would I be at if I went up or down? Where is that graph? Where is that function crossing at -3? That kind of help out a little bit? But we don't need to graph it. We can do it all mathematically. So everywhere you see an x, you replace it with -3. Come in here, I'm going to rewrite everything, but I'm going to put -3 plus 4 squared minus the cube root of -3, all divided by 4. -3 plus 4 gives me a 1, correct? 1 squared is just 1. And then I got this minus here, and I've got the cube root of -3. Now hear me out. The cube root of -3 is an ugly, ugly number, okay? It's going to end up being a really ugly irrational number. Remember when we talked about irrationals, okay? Like an infinite decimal. For this one, I'm not going to give you the infinite decimal. Now, if you were doing actual stuff like, say, for early childhood or for whatever else you are studying. You might need that ugly decimal rounded to a certain number, okay? But this one we can say, hey, f of -3 is equal to the cube root of -3 over 4. Because we simplified it, okay? Now, if you wanted to work it out in your calculator, could you? Yeah, I didn't work it out here. Good. So if you can do that one, do this one for me. I want you to change it into a function, okay? Change it into a function, and then once again, I want you to, whenever you get into a function, do it for x when x is equal to -3. You get that function? Good. Now evaluate it when f is equal to -3. Maybe you're wondering now, did you do that? Go, oh, hopefully, maybe some of you are going back to elementary algebra. Whenever you first learned how to go, hey, when x is equal to this, let's plug it in, let's learn why we do that. Well, now you're knowing why. This reaches all the way back to some of those very first lessons you learned in elementary algebra or Dev 2. Okay? Notation matters. Whenever we're replacing, we always put f of -3. We're letting ourselves know, or the reader, or the person who's looking at your stuff, of what we are evaluating at that moment. Okay? So we have negative. Now, be careful how you write this. Okay? Let me tell you this right now. This negative is not attached to that x. That is -1 times x squared. Okay? So you cannot do this right here and put that -3 in there like, okay, like this, and just count that negative in there. Okay? That has to be written like that. Okay, that's how that has to be written. That negative has to be on the outside of that parenthesis. Now, you do need to remember this, that whenever you're replacing, especially when you use your calculator, especially when using one of my yellow ones, or a tx, it needs to look like this, negative 3 squared minus 3 times negative 3. And there is a reason for putting that parenthesis. One, it's a rule, okay? But two, just to be honest, I can get real mathy on it, and I've shown you the math in intermediate. If you put negative 3 squared without a parenthesis, you're going to get a negative 9. That's wrong. We know that a negative and a negative make a positive, okay? But your calculator is going, no, 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 I'm going to do it this way. And it's because of PEMDAS, your calculator is seeing that that negative 3 is actually negative 1 times 3. And so it's squaring the 3 and then multiplying it by a negative 1. Wrapping it in that parenthesis, make sure that you get that positive number on the outside, okay? So what'd you get? Do the math to this one, okay? You're going to end up getting, well, this right here, negative 3 squared is just going to go to 9, right? Then I got that negative sitting on the outside of it, so that's going to give me a negative 9. Negative and negative make a what? Positive, so doesn't that just turn into negative 9 plus 9? So you should have got a 0. So that would have been a point. We would have said, hey, when x is negative 3, what is y? 0. So notice it is a coordinate point still. You have still solved for a coordinate point that's on a function, but it's just, we just said, hey, now instead of it just being limited to that, now I can plug in any point I want within reason. So how does it work when you see something on your homework? Well, look at this one. Use the graph below of a function f to find the value when f is equal to negative 2. Realize this, the negative 2 is your x value. And then you're just going to go to negative 2 and look. Look at the function and go, okay, what does y equal when x is negative 2? Okay, so at f of negative 2, we would come here, let's come over here to negative 2, and here it is right here. But notice what happens with the function at negative 2. So what would y equal there? Yeah, exactly. F of negative 2 would equal 0. I say this because on your homework, you're going to have some kind of weird looking answers, like weird questions sometimes. Like it may just give you this f of something equals something. It may say, hey, can you find the function? Well, yeah, because look at it. Couldn't I come over here and go, isn't this just negative 2 comma 0? Okay. And then do it again. How about, what is f of 0? Somebody tell me that one. When x is 0, what is y? Yeah, 9. Just go up to the 9. We start here. We know that's 0. Go up to the 9 right there. Okay, so here it is. It's 9. Or 0, comma 9. And you could do this all over the place. If I could show you the actual function of this, it's actually really ugly. I don't even know what it is. I do know, and you will too by the end of this class, looking at this one, I know it's negative, going down. Okay? Anything going down is going to be negative. I also know by counting how many times it goes across the x-axis, look, it goes across 1, 2, 3, 4, 5, 6, 7, 8. So it's negative x to the power of 8. Going down. Now, it's not just that. It's going to be negative x to the power of 8, and then just a crap ton of junk after that. Like all kinds of weird, probably even numbers, it looks like x to the 8, 6, 4, 2, I think. But still, I know the base function. Okay? Say that because that's what you're going to start learning. Okay? Now, one thing you need to remember is this. For vocabulary reasons. When we start looking at functions, notice we have f of x, okay, is equal to something, right? Realize this, your X values right here. That is the independent variable. Your Y is going to be your dependent variable. Y is dependent on whatever X is. Okay? Because remember, to get to that Y, where did we have to go first? X. And then go up to Y. You don't go to Y and then go to X. Okay, you have to go to X first. Now, and also good thing, just so you can remember, okay, because like I said, functions sound weird. Generically, we use f of x. As we go along in this class, I'm going to be using a bunch, okay, because I can't use two f of x functions, okay. And like I said, you guys are 1,000 times smarter than me. I know it. I know it. But I used to get so confused because some of your definitions now stuff are just going to contain f of x. Okay? And I always forgot to, f of x just means some function. There's a lot of different functions out there. Okay? So if you can just remember that whenever they start giving you a definition of stuff, this f of x could be a linear function, could be a quadratic function, could be a cubic function. You're going to see all the stuff to this. Just remember that and go, they're just talking functions. It's sort of like whenever I started trying to help you with demystifying some of these ugly words in math, like natural numbers or integers. Integers is a horrible number when you first start hearing it, okay? Yeah, when you realize, oh, it's just every number starting at 0, at -1, -2, increments of 1, 1, 2, 3. That's all an integer is. Real numbers, oh, every number. Okay, every single number except the complex numbers, which you know about now. That's all it is. So when we kind of demystify some of this, it does make math a little easier hearing, not maybe operationally. But at least whenever you hear something, you don't go, okay? So how do we know what to call a function? Well, if I have a graph here, instead of saying y, let's just call it, once again, h of t. Always realize what's inside, what is inside, okay? The parentheses is always going to be your independent variable, which is going to be your t here. So this would be h of t. Okay? Good on that one? Now, we can switch up notation sometimes, but we wouldn't have a function anymore per se. Okay? Like that other one we saw earlier where the parabola was on its side. Okay? That's not a function. Function is always a relation according to the x-axis. What would be the x-axis? It has to pass that vertical line test. It does not mean I can't graph things, though, like a parabola laying on its side. Okay? But that's whenever they're taking a function and flipping it. So instead of like f of x is equal to x squared, okay, it'd be f of y at that point. Okay? And they'd be making a y squared. So y squared would give you a function on its side. Okay? Thinking of that, you learn about circles in chapter 2 too. Remember that? Anybody remember the formula? Or what does a function look like? Well, it wouldn't be a function actually. We can put things in function notation so that way I can get a whole bunch of points. Okay? But it doesn't mean it actually works like a function. The reason we still put them in functions, remember, there are calculus students out there who will go, no, it's still a function because I can narrow it in. Okay? Anybody remember what that looks like? What the notation looks like for a circle? It's good to keep it. Remember, what is it? Just basic. You don't have to give me a big thing like
the x minus h squared, all the way squared plus the y plus k all squared equals r squared.
Notice what you're getting out there. You got an x squared and a what? And a y squared. You got two of them, right? You got two squares in there. Remember what I said? I go, hey, you get a one square going this way. You got a parabola. You say you're in. I know what you're thinking, and you're right. That is the equation of a circle. Go back and remember that because that one pops up a lot. It's always good to kind of have that one in the back of the mind. Okay. Are we good so far with functions? Okay. Let me go off on a tangent. Put down your notes. You do not have to know this, but for those, like I said, I have to teach you as if you're going to higher math because I don't know who is. Okay. For those of you who are not going to any type of higher math, then you can kind of go la la la. But this is good to know because of the notation that might pop up later on. Okay. Domain and codomain. Okay, notice the way those look. And the reason I'm teaching this, one, I took this class at this college. They did not teach me this. Okay. They blew past it. They didn't need you. And you don't really ever see it. You don't even see it in calculus 1. You don't even really see it in calculus 2. Calculus 3, it pops up. This notation pops up a lot. And I tell you what, I was lost. I was like, what the heck are they showing me? What is codomain? Because I'd only heard at that point what? Domain and what? Range. I was like, and there was no chat GPT. Okay. There was no way for me to go, okay, how do I, when you Google it, you get some really genius out there trying to explain it to you, and you're like, okay, I have no idea what this little Indian boy's telling me. Okay, this little 5-year-old Indian kid on YouTube, because that's, you know, so no, I couldn't understand it. Now let me read this to you. The notation F, A, B reads F defined from A to B, or F maps to A to B, implies that F is a function from the set A to the set B. The symbols indicate that the domain of F is the set of A. Okay, it's just a domain, normal domain. Okay, X values. And that the range of F is a subset of B. Okay, in this context, B is often called the codomain. Okay, so notice here, it says this first one. F maps from the real numbers. We know what real numbers are. It also maps over to the real numbers. It's basically saying whenever I take this function, if I plug in a real number, you know what's going to come out the back end? A real number. That's all that's saying. Yeah, it took me like 3 months of really studying for that finally kind of clicked. And even right now, I might be kind of simplifying it too much. That's fine for right now. Okay, now codomain says this. Right here says, hey, real to real by f of x is equal, they give you a function. That means if I plug in a real number to this function, x squared, which we know that creates a parabola, I'm going to get real numbers out the back end. Okay, by this function. Okay. Hear me out. I have a domain here. Here's my function, right? More or less. Math is good. Domain, all real numbers. But yet this base function here, let me draw a little bit better. Base function. Now, mind you, I'm not getting fancy with this function. It is very hard to draw on this thing. I dare y'all to come over here and try this, okay? I broke it last week. That's how come it wasn't working, because I tried to pull it forward and I didn't realize I ripped out a cord. No, they can buy bigger cords though, so I'm just telling you. So notice the range of this guy would be 0 to infinity, right? That makes sense to everybody, okay? But I just gave you the range, okay? What this is saying, they're both saying this. If I have a domain here, here's my x values, right? My domain says I can put any real number I want, right? Can we all agree? That's what the graph is telling me. I can put any real number. Now, the codomain is this. The codomain is also all real numbers. Here's your range. Inside that are more numbers, right? Can we all agree that on the y side, there's a lot of numbers? But I can't use every number. I can't plug in every single number into this function here and get out every single number. That's not the way this works. I get out a certain subset of numbers. There's your range. The range is these little bit amount of numbers right here from 0 to infinity. That's what that is saying. Okay. Now, this one right here is saying when I plug in a real number and I get a real number, that's fine. It's just saying you're getting real to real. You're mapping from the real numbers to the real numbers. Notice the next one. Notice what's different. I'm mapping from the real numbers to, well, doesn't it look a lot like my range? My actual range for this function, the actual range. Can we all see that? When that happens, okay, when you see that, okay, that is called, you don't have to write this down. Remember, this is not going to be on your test. Okay, there's a special mathematical, two special mathematical words. We say this function is onto, or we'll call it surjective. It's when you map to the actual range of the function. When what you're mapping to matches your range. Here, that doesn't match. We know my range is in there, but it's not the same. And there you go. Now, you know, it's a pretty deep math right there. You don't have to, you're not going to be tested on it, okay? But it is good to know because you will see things that look like this. You'll see like another function, g of r mapping to the complex numbers. And they'll give you some sort of like, you know, function by that. They'll be saying whenever I plug in this real number, what's going to come out the back end is going to be a complex number. Okay, it's letting you know the behavior of the function you're dealing with. Okay, which is nice going into it. But there's also something called, now this you are going to be tested on, implied domain of a function. Not that bad. Okay. It's a lot, it's an ugly name that means something very simple. Now, before I show you what the implied domain is, I want to go through some quickie review with you. If I give you a function, I'm going to start writing everything as a function now, okay? Reason being is this. If I gave you something like this, 1 over x is equal to 3. Well, okay, I cannot, let's not do that one. Let's do 1 over 3. Sorry, 1 over, I wrote that wrong, sorry. 1 over x is equal to 3. You can solve that. Hence solve, right? Notice my wording, solve that. Because I can multiply that 3 up, right? Multiply that x up, you get 3x, divide it, there you go, we can solve for x. We get a value. No worries. Don't have to worry about anything. But let's be honest. We're not doing that now. We're going to do this. If I showed you this, f of x is equal to 1 over x, you should know by now that whenever you see f of x, what is that? 1, it tells you, are you just restricted to one value of x? What x's are you allowed? Are you? Remember, the function is a machine. Some functions, now here, you can think of every single function, remember I said shape, think of every function like a machine, like a printer. This right here is a function. Okay, so here's my little machine. So this printer takes paper, right? So basically what it's saying is no matter how much paper I put into this thing, it's going to work, right? But what if I put in like a piece of paper, but that paper was made of like, say, tissue paper? What's going to happen to this function? You think tissue paper is going to work through this printer? Probably what's going to happen to the printer? It's going to get jammed up. Something's going to go wrong. So some functions don't take everything. They're going to go, whoa, 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 you can't give me everything. Not everything works with me. What's not going to work with him? What would jam this function up? This 1 over x. What is the restriction?
X, 0.
0. You can't divide by what? Because if you divide by 0, what do you get? Prove it to yourself. Put in your calculator real quick. Do 1 divided by 0 and see what you're going to get. You're going to get domain error. Okay, and that's an error. That's a function going, hey, I know that you learned that you can give me anything. You can't. Some functions have a restriction and they say you cannot give me this value because I have no way of working. You're going to jam me up. You're putting tissue paper in a printer machine. Okay, so this one has a restriction. It says x cannot equal 0. Give me any other number, man. I'll work great for you. I'll work from now to forever. But you can't give me this number here. Same thing. If I showed you f of x is equal to the square root of x, about half of you more had me in intermediate. There is a restriction on him, isn't there? Because what is my index for this one? It is obviously a what? It's a 2. More importantly, it's what? Even. Even roots have a restriction. What can they not be? Yeah, the inside, the radicand, that x can't be negative. Don't start thinking they can because we created complex numbers, because even complex numbers don't allow negatives. We pull the negative out and make it an I. So we free up the x. Okay, so this one right here, but now can we have 0?
Yeah.
Yeah, because the square root of 0 is just 0. So here you have x is greater than or equal to 0. Are we kind of remembering some of this now? Some of this kind of being, okay. Well, let's do one more real quick. What do I give you another function of let's do a cube root of x. What's its restriction? Exactly none. Because when you have an odd index, you can have anything you want. And graphically, when you see these in 3.3, you're going to go, oh, that makes more sense since I'm seeing this by the graph. I can understand why I'm allowed negatives. Okay? So here, x can be all real numbers. So you're not restricted. So there is no number. So notice your most free function is that one right there. It's like, give me any number. I don't care. Throw them all at me. You want to give me negatives? Give me negatives. I don't care. I'll take them all day long. But the other two say what? Give me any number except that number, because that's like putting tissue paper in me or whatever. Okay, because I'm going to give you an error. I'm going to give you an error message. I'm undefined at that error. So this is how hard it is. No matter how ugly the function is, which, let's be honest, this one right here, pretty ugly function, isn't it? You got f of x is equal to the cube root of 4x, the square root of 4x plus 24 plus 3. I only care about that I'm dealing with a square root. A square root is an even root, an even radical. Even radicals always have a restriction, and that means the inside can't be negative. So you take out the inside right here, and you go, okay, well, I've got 4x plus 24 has to be greater than or equal to 0. Solve it. 4x is greater than or equal to negative 24. Divide off the 4, and I get x is what? Greater than or equal to what? Negative 6. Now be real careful. How are you going to mess this up on your midterm? That word right there. Interval notation. If that interval messes you up, okay, first off, we all know the alligator mouth. The alligator eats what's larger. Okay, here's another little hint. Notice, look at where I'm drawing here. He's eating in this direction, right? But look at where his butt's pointing. So that's the direction your line would be going. Okay, so if I decide to graph this just really quickly, I could put a negative 6 right here. Because I have an or equal to, I'm going to go this direction and then close it off. And so there's my interval notation. -6 to infinity.
What about the +3?
Don't need it. This is why we call this an implied domain. We don't care about that. We're just worried about this. Let's go with that. I want to go with what she said because she asked a good question. Well, what about the +3? Isn't that going to help that guy out? No, because if I end up with a negative here, it doesn't matter what happens outside this thing because now this has become undefined and I can't work out anything else. That makes sense? Okay. Because you try to do it, it's like, oh, the function machine shut down. It's like, I can't do anything else until you fix this problem. It's sort of like I can grade papers all day long, but if my computer shuts down, it doesn't matter. Okay. Until I can get the computer working again, it doesn't matter what's happening on the outside or what's happening around me. Okay. Knowing what you know there. So you're always looking for the function inside of all that mess, the function that would have a restriction. Some functions don't. X squared? How do you know? If your domain is all real numbers, you don't have a restriction. Makes sense, right? Okay. And especially once you've graphed these. Every single one of you to get in this class, you've had to graph these. Okay, so your graph for this one would have looked like this. You have a y, you have an x, here's the -6. Remember, it would have looked like this. Well, isn't that everything? Can't have anything over here because there's nothing there. There's no function there to graph to. Good? Okay. Do the other one. Tell me what the implied domain is of this one right there. Implied domain. Okay, don't get hung up on that one. Okay. It's your domain. Okay, what that guy is. How do you know there's a restriction?
Denominator?
Exactly. Anytime you have a variable in the denominator, you're going to have a restriction. Because since we're dealing with functions, the function machine says, give me any x. But this one's going to come with a big red sticker on the back of it going, I realize I advertise myself as give me any x, but please don't give me this. You're going to break me. Thank you for buying me. Okay, so this one, once again, you're going to say, hey, I'm going to take that out and go, well, look, I don't care about the top at all. Not one bit. Because the numerator doesn't tell me anything. The numerator can be 0. 0 divided by anything is just 0. That's fine. Think of your slope. Okay, y equals something's fine. X equals something, that's an undefined slope. Okay? So look at this one here. That helps. Remember, think of slope. Okay? You have 8 minus x cannot equal 0. Well, how about we subtract 8? I get -x cannot equal -8. And then divide off a -1. And then I get x cannot equal what? 8. Exactly. But that's not your answer. Is it? How would you write that in interval notation though? Now think about it. Think hard. I cannot equal 8. There you go. But you can equal what other number?
Everything.
Everything else. I don't care how negative you go. I don't care how positive you go, but you can't equal this guy right there. Okay? So always going to negative to your left. Okay? And then I'll put 8. Then a union. 8. And then an infinity. And notice what this says. I always read left or right, so I'm always coming from negative infinity. I get up to the 8, but I can never touch it. Because if I do, that means I equaled it, and that means I just got 8 minus 8, and can't do that. I get a 0, it's undefined. So I get a little bit past 8, but I can't equal it again, and then I go off to positive infinity from there. That's your union. Why is this important? One, as we move forward in this class, we get into chapter 4, you're going to start learning the behavior. Kind of what you're learning now is the behavior of functions. What's happening? When are they at their lowest? When are they at their highest? What direction are they going? How are they acting? When are they skinny? Usually in the summer, we walk more. When are they fatter? During the fall semesters, when we have to teach more and can't work exercise as much. Okay? Now, last thing. Stay with me on this. I'm gonna finish it off pretty quick. Remember, when you have a function, you replace everything, whatever's inside the f of whatever that junk is, you replace it for x. Look at this right here. Given the following function, determine the difference quotient. You have f of x plus h minus f of x. They give you f of x. F of x is this guy. Okay? Realize it's just saying, hey, wherever there's an x, I put an x there, right? Does that make sense? All you're doing here is taking that x plus h and also putting it in. Watch how I'm going to write it. Welcome to calculus. This is actually a calculus problem. Here's the sad part. I'm going to show you this. If you ever take calculus, you're going to hate me because I hated this when I learned this. I was like, dude, there's an easier way. Yeah, you can do these in your head. Okay. Watch this. Watch how I do this. Now I'm replacing. First things first. Just hear me out. I get it. This is where I got lost. Even whenever I took this class, I was like, what? First part, I'm replacing this, okay, and rewriting the whole equation with that in there. So watch what I put. I put x plus h squared minus 6 x plus h plus 2. Isn't that what it just said? It said, hey, you have an f of this. But then it says this, don't forget you got a minus there. Okay, we'll put my minus. But anytime we have a minus sign, what better go up next?
Parentheses.
So put a parenthesis. Now it says put f of x, which is just our original function. And then we write x squared minus 6x plus 2. All of this over h. And then you just do the math. You're going to start cleaning it up, okay? If one, okay, I know it looks hard. I give you all the notes to it, okay? But I'm going to go and kind of do it pretty quick because I got 6 minutes. When I FOIL everything and distribute, because that's all I'm doing right now, right? FOIL everything and distribute, I'm going to get this. X squared plus 2xh plus h squared minus 6x minus 6h plus 2. That was all of that. Split up and FOILed, okay? Because remember this little x plus h, you got to rewrite that twice. X plus h twice, right? And then FOIL it. And then I'm going to take that last part and I'm just going to take this negative and distribute it in there. Come in here and I'm going to get negative x squared plus 6x minus 2 all over h. But watch what's about to happen. This is why we call it the difference quotient. What you're doing now is the precursor to what we call the derivative. This is why they call calculus 1 differential calculus. It's learning to take derivatives. You know what derivatives? A slope. I'm finding the slope of this function. Okay? But it's the instantaneous slope at a specific point, not the average slope that you guys are used to having. Okay? There is one caveat, doesn't deviate completely. But look at this carefully. Notice I have an x squared here, a negative x squared there. 6x, positive 6x. I have a positive 2 and a negative 2. Oh, well, look at how much cancels out. A lot of it will cancel out. Okay? And then we come in here very carefully and then look at, this is how you finish it up. I have 2x to the h plus h squared minus 6h, but realize I can put every single one of these with that h. Remember, when you have the same denominator, you can do what? Split that denominator up into each one and then come in here and go, hey, how about I get rid of that h there? How about I get rid of this h? And then how about I get rid of that h? And then notice you're just going to be left with 2x plus h minus 6. Another way to see this one is if you have that 2xh plus h squared minus 6h all over h. Can you also notice you could have factored out h, right? How many h's? Just one, right? And that would have done the same thing. Not too bad. You realize how I did it? All I did was this. I said, hey, one of my functions I have to make look like this now. Instead of just the x, I'm going to say x plus h. It's going to be the same thing for this one here. Look, I'm just going to come right in here and go, okay, determine g x plus a minus g of x. Well, they give me the g of x. G of x is a function. Okay, well, there it is. G of x plus a is just another function. They're just telling me, hey, I'm going to give you something extra. And you're literally going to come here and go, okay, well, g of x plus a is going to be that whole thing written out with that. So I have -5, well, x plus a squared minus 3 x plus a. Right? And then they're saying you're going to take all of that, and then you got this other g of x here, which is just that guy. And you're going to take this -5 x squared minus 3x, and you're going to take all of that and go, okay, hey, -5 x plus a squared minus 3 x plus a minus, because of that minus, I'm throwing up a what? Parenthesis, -5x squared minus 3x. And now you're just in cleanup mode.